Hey there, good afternoon, good morning, good evening, wherever you are in the world. My name is Chris Down. I'm an engineer at Facebook on the kernel team, mostly working on Linux kernel memory management and especially a feature called Cgroups, which, as you may have guessed by the title, is what we're going to be talking about today. I'm also a maintainer of the systemd project, mostly working on resource control, things like that, things which are related to Cgroups, memory management, that kind of stuff. Most of the time, I guess my job at Facebook is thinking about how we can make Linux more reliable and more scalable. We have 1 million plus machines now, and we can't just buy more RAM. We can't just magically increase capacity by adding it. So we need to extract the absolute maximum out of every single machine in a safe way. And that's the kind of topic which I want to talk about today, and basically want to go over how over the last 5 years we have increased Facebook's reliability and capacity using these primitives introduced in Cgroup v2, and how you can apply that to your workloads and your organization in a way that makes sense for you. So I think many of us at leading edge companies do have this trade-off of capacity, performance, and reliability, and it's a really uneasy one. At Facebook, for example, we have good problems. Our user base is increasing, our product range is diversifying, but with that growth comes scaling problems of a nature which we've not really had to deal with before, and we're really feeling a crunch for capacity. And we simply can't effectively solve these scaling problems by throwing hardware at the problem. We can't construct data centers fast enough. We are running on clean power. We can't necessarily get clean power easily enough in everywhere across the world. And we have 1 million plus machines now, and we just cannot afford to waste capacity because any small loss is a huge absolute loss across the fleet. Ultimately, the point here is that we need to use resources more efficiently, and we need to build the kernel infrastructure in order to allow us to do that at scale. Another challenge that we have is that many huge site incidents are actually caused by lacking resource control. So not being able to readily control things like CPU, memory usage, I/O, that kind of stuff. It's actually caused some of the most pervasive and huge issues and outages for large companies like us. And we need to sustain and support an initiative industry-wide in order to actually solve this problem once and for all. So how does all of that talk about capacity and reliability manifest into this cgroups thing, which this talk is ostensibly about? Well, cgroups are a kernel mechanism to balance and control things like memory, CPU, I/O, that kind of stuff. And I'm sure if you've operated containers before, you've probably seen their name floating about. Every single modern container runtime, Docker, CoreOS, Kubernetes, systemd, you name it, it uses cgroups under the hood. It doesn't do all that stuff by itself. And there's a reason for that, which is cgroups solve a lot of these long-standing problems with classic Unix resource control, and there's no reason for them to reinvent the wheel. Cgroups have existed for about 14 years now, and they've changed a lot in that time, actually. Most notably, 5 years ago or so, we released Cgroup v2 in kernel 4.5, and I gave a whole talk at around the time that we released it on why we were moving to Cgroup v2, why we weren't just making incremental improvements to v1. And if you're interested in a really, really in-depth discussion, that talk is still a really good resource. I think it very well represents the thoughts that we had at the time. But for now, let's touch on, the most fundamental changes that made Cgroup v2 a step change in the paradigm, rather than just an incremental improvement on what we already had. So the first major change is how we organize cgroups themselves, actually. And this is more than just an aesthetic change. It actually allows us to do some things that we've never been able to really do before, technically. Fundamentally, this reason is the reason why we had to move to Cgroup v2 instead of making a Cgroup v1.1 or whatever. So it's certainly worth going into in some detail so that you can understand why we did that. If you've had some interaction with cgroups over the past few years, you probably have been using Cgroup v1 until quite recently. Version 2 has been working great. It's a game changer for resource control, but most distributions were fairly worried that some applications, like Docker, for example, didn't support Cgroup v2 yet. Now, though, pretty much all of them do. I'll go over a list at the end. And Fedora, in fact, as a distribution, moved to Cgroup v2 by default since Fedora 32. So it's clearly operating well at scale. And that was a pretty nice poke to those who still hadn't, implemented Cgroup v2 support in their containerisation engine, even after, several years to kind of get it there. So I really appreciate Fedora doing that. In Cgroup v1, sysfs cgroup contains controllers as directories at the top level. So you see resources like CPU, memory, PIDs, you see them as a directory inside sysfs cgroup. And inside these directories are hierarchies for each resource. So for example, inside the PID cgroup hierarchy, you see, for example, files which would manage the maximum number of processes in a cgroup. And inside there, we have a hierarchy of directories. You can build up some cgroup hierarchy, and each directory contains these files for PID management. If you don't know if you're using cgroup v1 or v2, if you go to /sysfs cgroup and see, directories like CPU, memory, block IO, it's a dead giveaway that you are still on this legacy v1, which is basically frozen in time and we are not really supporting anymore. So here is a concrete look at how this all looks in cgroup v1. So the cgroup file system is typically mounted at /sys/fs/cgroup. Inside you have a directory resource like memory or CPU, and each resource maintains its own distinct hierarchy. So you can have a single PID, a single application, in cgroup foo or cgroup A in one resource, but in cgroup bar in another. And this flexibility of being able to have different hierarchies for every single resource and being able to put PIDs in different cgroups per resource has some pretty negative technical effects, which I will come back to in a short second. The fundamental paradigm of cgroup v1 is that cgroups only exist in the unique context of a resource. There's no one cgroup for a task on a machine, and it's totally possible, as I mentioned, that a PID can be in group A in block IO or in CPU, and group B in memory, for example. By contrast, in cgroup v2, we don't actually see the resource directories at /sysfs cgroup anymore. We see the directory for the systemd units themselves, not any resources at the top level. So how does the cgroup hierarchy know which resource it applies to? Well, the answer is that the way that this works is essentially inverted. Now cgroups are not created in the context of a particular resource, but resources are enabled or disabled for a particular cgroup. And we have one hierarchy, one unified hierarchy, another name for cgroup v2, which rules them all. And this means that you explicitly opt into, for example, the CPU controller for a particular part of the cgroup hierarchy. And once you've opted into the cgroup, we give you the files which would allow you to control that particular resource. So in cgroup v2, we now have this unified hierarchy, which means that cgroups are global. A PID is in exactly one cgroup on the entire machine, only one, and it shares that cgroup between all resources, memory, IO, CPU, etc. So instead of having a cgroup per resource, you now have resources per cgroup. So the idea here is that you or your container or init system opt into some subset of controllers using the cgroup.subtree control file. You might write plus memory or plus CPU, and you get the files which are related to controlling that particular resource. This might seem like a purely aesthetic change, going from a cgroup directory in each hierarchy to one where you enable resources down the hierarchy as you want. However, this, as mentioned, has quite significant technical advantages. The most major one of them, and the reason again why we couldn't make a cgroup 1.1, is because when you write to a file in Linux, what happens? It seems like a softball question, but it's actually not. It's actually somewhat complicated. So you don't really write to the disk, right? For performance, you write into the page cache and you create a dirty page, a page which must be later written back to disk. So at this point, your write syscall has probably returned to your application with success. Your application can continue going about whatever it wants to do. But the process isn't really over. Eventually, that dirty page does need to be written back to the disk. But when does it get written back to the disk? Who writes it back to the disk? The dirty pages here were made for a particular application, your application which is called write, and the flush to disk will be performed on behalf of that application by a kernel worker or a K worker. And this could happen an indefinite amount of time after the write syscall returned. In cgroup v1, these went to the root cgroup, which is essentially the I don't really know who's responsible for this cgroup. It's essentially limitless. And for most workloads, these page cache write blocks are the vast majority of I/O being performed. This can also account for a huge amount of memory on some workloads. So not accounting for these means you're missing from your accounting a huge amount of information. You're missing a huge amount of stuff which you actually would like to limit or throttle back on. And it's impossible to track or control. So having this new unified hierarchy in V2 is what makes tracking these multi-resource actions possible. In Cgroup 1, you could be in Cgroup A for I/O, but Cgroup B for memory, which, as I mentioned in the previous couple of slides. But since a cgroup is the unit at which we charge out, much like a page is the minimum unit for a memory, a cgroup is the minimum unit for a cgroup charge, we can't make any assessment in Cgroup V1 about the relationship of Cgroup A in one resource to Cgroup B in another resource. And for these kind of multi-domain actions where, we write a page into memory, we're waiting for the I/O to happen, and it spans multiple resources, we just drop the charges on the floor in version 1. So in Cgroup V2, we're actually able to track these and map the request back to the originating cgroup. So we're actually able to count these towards cgroup limits and take the appropriate action. For example, we can understand the relationship between I/O and memory for a write-back. We can not only hold back some of these allocations if they are too costly, but we can also perform reasonable actions based on I/O or memory pressure inside a cgroup in the context of a singular cgroup, which we couldn't do in V1. We can also do things like charge the cost of network activity to a cgroup after the fact. That might sound really trivial, but actually it's quite complicated because network has this weird paradigm, right? Network and CPU, first of all, are two different kinds of resources. And again, it's another example of a multi-resource action, which is something which we only really support in V2. But network has an even more insidious property, right? Which is when network packets come into your card, you don't really know who it's going to yet. It needs to be routed. It needs to be assessed and determined by the kernel which application is going to get those packets, which application is going to get the data. So you don't really know who's responsible at the time that the CPU or most of the CPU is taken. But with Cgroup V2, we can go back and look and charge the resources spent at the point which we find out who the packets are for. And that allows a lot better monitoring and resource control because that can be a really non-trivial amount of CPU for some workloads. So Linux 4.5, which is when we made Cgroup V2 essentially a public-facing API that anyone can use, was released over 5 years ago. So at this point, you might be asking yourself, if this was all merged like 5 years ago, what on earth has been happening since then? Why is he coming to talk to us about it now? So in this talk, my hope is to show you how the best intentions can often result in not ideal outcomes, and our path to take the extremely complex realities of kernel resource management and present them in a way in which people can actually understand and use at scale. What's being presented here is really the state of the art in resource control. My ultimate hope is that by the end of this talk, you'll have a better idea of why controlling memory or CPU or I/O is so complicated. And hopefully you'll come away with a few ideas about how you might want to apply this to your own organization or your own workloads in a way that makes sense for them. So back in 2016, when we released it, we only really had one real user of Cgroup V2, which was us. It took a lot of work and overcoming obstacles to reach where we are now, where Google and lots of other companies are using it or seeking to use it. And we had a bunch of cool and new primitives back in 2016, which we wanted to use. But when we actually went to go and use them, it kind of ended up something a little bit like this. The primitives aren't entirely wrong. They're still kind of on the right track. But we need to work out in which cases we should make the operating system a little bit more square or our primitives a little bit more round in order to achieve the goal that we actually want. And knowing which of these makes sense in any given situation requires spending quite a lot of time in prod, gaining experience through a significant amount of testing, experimentation, and working with others to see what they're seeing on their workloads. In the end, we really had to design new tunables for memory, CPU, and I/O from the ground up to achieve what we want compared to 2016. And a lot of the paradigms which we take for granted inside Facebook and other large companies now simply didn't exist 5 years ago in Linux. So what does that mean to reinvent how we think about doing resource control from the ground up? Well, one thing which is critical to understanding how Linux manages memory is that it has different types of memory. From the CPU's perspective, there's really not much difference. It has some kind of idea about permissions or stuff like that, but it doesn't really treat them as semantically different, whereas Linux does. For example, anonymous memory is, as the name implies, not backed by any backing store. Memory explicitly allocated during the program allocation by malloc or similar paradigms is typically anonymous. And most people also know about caches and buffers, two sides of the same coin. They've been part of the unified page cache for many, many years now, so I'll probably just call them file cache from now on. But if you ask most Linux admins, they will say that page caches and buffers are reclaimable, which is not wrong, but the problem is that a lot of Linux admins have this misconception about what reclaimable really means. It doesn't mean that you will definitely be able to reclaim it. It just means that you might be able to reclaim it at some point if you happen to ask nicely and we are in a good mood at that particular point in time. So, for example, if some application is absolutely hammering some file, it's very unlikely that we would choose to drop it from cache, because the performance will just get driven completely into the ground, right? So while they can, under some circumstances, be trivially freed, it doesn't always have to be the case, and it's not necessarily the case for whatever ones you're talking about. And this can cause some confusion when people ask, why did my application why did the killer come along when I still had this free memory? And we'll come back to some of these more unexpected foibles around what people consider free but isn't really free in a little bit. The fact that these caches and buffers can be essential is also an example of why RSS, which is a metric that we love to measure as an industry, is really kind of bullshit. RSS often unduly skews a lot of attention towards a very small select number of types of memory, anonymous file memory and mostly map file memory. We forget, though, that many workloads simply cannot sustain any performance or operate without extensive file and buffer caches or other system-wide shared memory. The reason we measure RSS as an industry is not because it means anything really useful, it's because it's really easy to measure and really stable. This is a really poor reason to measure something. So when somebody asks, how much memory your application actually uses, the only sensible answer, unless you've compressed it until performance is degraded, and we'll go over how you can do that a little bit later in the talk, is that you really have absolutely no idea how much memory your application uses. As an example, in one case inside Facebook, we had a team that for years believed their memory footprint was roughly 100 to 150 megabytes on the fleet. And using our new metrics, which we'll go into in this talk, they discovered it's something more like 2 gigabytes. That's a huge absolute gain, right? That's a huge thing to not know for so many years, and it probably explains some of the things that we've seen at scale. So this is one of the reasons why inside modern resource control, we typically limit all types of memory together instead of just, trying to limit anonymous memory or trying to limit RSS or whatever. Because if you just limit one type of memory, if you just limit, say, anonymous memory and ignore the page cache, for example, you're going to trivially allow one application to still kill all the performance of the others because, again, the memory is not free. So this is why in Cgroup 2 we limit and account for all types of memory together. We still have this memory.max file, which is not based on RSS. It really is limited based on everything that you do inside a Cgroup, everything you allocate. And this is a step change from the era of, per process limits or Cgroup 1, which only limits on a subset of memory types. In Cgroup 1, there are 50,000 different types of memory limits you can set. But the problem is you can't set any absolute memory limit to bound the Cgroup. So on the surface, this memory max stuff looks like it should work reasonably well, right? And it does. It does exactly what it says on the tin. There's nothing wrong with it in terms of what it declared it was going to do. It sets a maximum amount of memory which is allowed to be consumed in the Cgroup, and it does that fine. The problem here is how you actually use that to compose a reasonable and reliable system. So let's say that you have a couple of slices. You have a couple of different groupings of applications. So you have your best effort applications in a slice called best effort.slice. It makes sense, right? And you might put things there like configuration management, metric collection, that kind of stuff. Things you'd really like to have running on your machine. But if the workload is absolutely, is being destroyed, then yes, we can live without them for a bit. So the workload, on the other hand, consists of applications which you really do want to serve on this machine. So, for example, it might be HHVM on a web server or MySQL on a database server. And you can have multiple workloads on a machine, of course, and we'll come back to that in a bit. But for now, let's stick with one for simplicity. So if this thing is not running, the machine is useless. That's what should be in the workload slice. So the typical system administrator at this point, being responsible, might have a way of thinking that goes something like this. So you're scared that non-system applications might kill things. They might invoke the killer. They might degrade the performance of the workload. So you put those non-critical applications in system.slice and set a memory.max. Oh, but now you're worried that some particularly badly behaved application is in there. So you might want to set a memory.max for that particular application so it doesn't affect all the other applications. Oh, but now you're worried that your main application might cause, a global and slow down the machine as a whole. So you want to set one there as well. You want to make sure that you don't get global you only get a Cgroup and so on, until you end up with a bunch of impossible to reason about limits sprinkled all over the place, which you can never really reevaluate in the future. And inevitably, one of these applications is going to legitimately grow a bit, and it's going to be an absolute pain in the ass to reason about resource distribution again and what on earth these numbers mean and how you should adjust them. And this is even infinitely worse if you work somewhere like Facebook or Google, where we have thousands of services and there's no one person who understands everything that runs on a machine. So our ultimate goal here is, just to keep whatever's in workload.slice running, right? That's the important thing on the machine. So what if we could just encode that instead of sprinkling memory.max everywhere and causing a headache for the system administrator? What if we could just write something like this? So memory.low is a fundamental change to the way that we've gone about controlling memory on Linux and Unix as a wider thing for the past 50 years on Unix. And the idea is that instead of trying to control memory by putting every application into this very tight coffin of you're going to use exactly n megabytes and you cannot even go a page over, instead we should just say, how much applications in a cgroup which we want to protect need to operate and let the system sort it out. Sounds great. How does it work, though? How does that actually work? So all of this works based on reclaim. So reclaim is this process of trying to free pages, either in response to a global memory shortage where the system is generally under a lot of pressure, or brushing up against limits within a cgroup like memory.max and trying to get it back down again. So memory.low hooks into the kernel's reclaim infrastructure in order to protect some memory for a cgroup. For example, if you have memory.low equals 20 gigabytes, as long as you are using below 20 gigabytes of memory, you'll generally be completely exempt from being reclaimed. You'll generally not have pages freed from you. And the only time we'll dip into memory.low reserves is if there's an immediate global memory shortage. And you can see when that happens by looking at the memory statistics which we provide in the cgroup directory. This might sound kind of simple, but in reality it's actually fairly non-trivial to implement. For example, if multiple different levels of protection in the cgroup hierarchy are competing against each other, we have to decide what to do. We have to decide how much protection we allocate to each one. And we also have to decide, how to distribute protections from a parent to a child, especially when its children are competing with each other. We also need to handle the case where, you're slightly over your memory protection, but we don't want this binary behavior. If you go one page over and we just reclaim and so on and so forth, and we bounce back and forth. So on modern kernels, we have this mechanism to reduce the reclaim proportional to how much of your workload is protected at any given time. So another nice effect of this is that this is a lot more work conserving. Work conserving is just a fancy term to mean as long as you are not dipping into what the workload needs at any given particular moment, you can use as much memory as you like. Even if you are in the best effort slice, you can grow as much as you like as long as you are not affecting the workload. This is much more tolerant of temporary spikes and changes in memory composition on the system. We're not reserving those 20 gigabytes for the workload. We are just saying, if the workload happens to need it, we're going to aggressively give it to it. So inside Facebook, we are now primarily reliant on memory.low protection rather than limits in production at Facebook. And there are some more niche use cases for limits, which I will go into one of them in a second. But at the fleet level, we have mostly transitioned towards using these protections instead of punitive limits. So that said, let's go into one use case where these limits actually can be used for something useful. So one of the more common things which happens when people move to Cgroup 2, and I tell them, my usual spiel about don't use RSS because it doesn't mean anything useful, is that they go and set up a limit based on memory.current. Memory.current is a file that, as you might guess, shows the current memory usage for a particular cgroup. But it's quite important to understand what that means. So the very fact that we're not talking about RSS anymore, but all kinds of memory used by the cgroup, means that the ramifications for this are different and the meaning is different. So it includes things like caches, buffers, socket memory, kernel objects allocated based on the application's usage, and anything like that. So All of this is in memory.current, and that's exactly how it should be, because that is what we account for and what we limit on. As mentioned earlier, though, the reason that people choose RSS to limit on is not because it's something good to measure. It's because, it's relatively static. It doesn't really move around a lot. It's easy enough to set a limit on, and it makes you feel pretty good at night, I guess, even if it doesn't do anything particularly useful. So memory.current suffers from exactly the opposite problem. It tells the truth, and people don't know how to handle the truth. For example, if you set an 8 GB memory.max, let's say, and your application runs for a little while and there's no global memory pressure, the system is generally not contended at the global level, what is your memory.current going to be? It's going to be 8 GB. We're going to expand to fill like the memory which we've set as the limit for the cgroup, because there's so much slack, right? There's no reason for us to get rid of all this nice file cache, buffers, all that kind of stuff. It's not that your application really needs 8 GB, but the fact that Linux is passively populating, the page cache and other nice to have things, and if there's no pressure for it to shrink from outside forces, then we're just going to expand until it reaches the limits. So what should we do? How should we know what the real amount of memory needed is at any given time? And again, you can't just get that from RSS. We just don't have this metric in Linux at this point in time. So to answer this question, we need the assistance of another technology which was invented at Facebook. So let me ask you a question which might seem kind of easy, but have a think about it. It seems like a softball question, but it's actually kind of complicated. So how can you tell that you are running out of physical memory before it happens? It's actually kind of complex. So have a think about that. If I were to ask you, is your machine oversubscribed on memory? What kind of metrics would you traditionally look at to determine that? So one of the things which, if you are, more new to Linux, you might say is, I want to look at the free memory. I want to look at the free memory, or free memory without cache and buffers. But the thing is that doesn't really tell us, how much memory is actually required. That is, having your memory, fully in use doesn't typically necessarily imply being saturated, just like the, expanding to 8 GB case that we just mentioned a moment ago. Another metric which you might bring up is something like, page scans, the rate at which we are trying to free pages. If your page scans are high, it could mean that the system is kind of oversubscribed on memory, but it could also mean that your system is operating in an ideal state. It's really hard to tell just from that what exactly the situation is. So it's not easy to tell from these kind of metrics alone what exactly the future holds, whether we're about to go over the cliff or whether things are generally pretty stable. So usually all of these metrics which we come up with are just approximations of memory pressure. So what is memory pressure? Well, we've never had a metric like this in the kernel before. We have many related metrics like memory usage, page cache buffer usage, but even with all those kind of metrics and the ones we went over earlier, it's really hard to determine, is this ideally used or is this oversubscribed? For example, in memory in PSI, like the idea here is to use some metric to determine how long we are being stuck on the system doing memory work, which we otherwise wouldn't have had to do if there was more memory on the system. So some here means that some threads on that cgroup were stuck in memory work for, say, 0.21% of the time in the last 10 seconds. Full, on the other hand, it means similar, but it means all threads in that cgroup were stuck on the memory work. They all couldn't make any forward progress because they're stuck on memory. So this could be things like, waiting for a kernel memory lock. It could be being throttled. It could be, waiting for reclaim to finish. But even more than that, it could be really dominated by this memory-related I/O, like, for example, refaulting file content into the page cache, doing swap-ins, that kind of stuff. And pressure is essentially saying, if I had more of this resource, I could probably run n% faster. In this case, I could run 0.21% faster. This can also be really useful to you in developing high reliability or high availability applications. For example, we use this to know in advance when we are using too much memory and do load shedding, backing off requests, that kind of stuff in some services. We also use it for our user space preum detector, UMD, which has a really fine-grained policy engine and decides what to prioritize on the system in the case where the memory gets oversaturated. We use it for all kinds of things, not just in Facebook, but Android and many others are also using it for resource contention detection. And you can't just get that by measuring memory, because again, or resident memory, because again, you don't really know which things you can reclaim, which things you can free, until you actually go and try and do it. And that's why memory pressure is so powerful. So how does this all relate to the case which we mentioned earlier, where we, have some slack in memory.current and we want to work out what the real memory usage is? So let's take an example kernel compilation job, which with no limits has a peak memory.current of just over 800 megabytes. However, when a memory threshold of 600 megabytes is applied, actually the job finishes in roughly the same amount of time, with 25% less available memory. The same even happens when we go down to 400 megabytes, and we're now using half the memory which was originally used at peak by the application, with only a few seconds more wall time in the compilation. Pretty good trade-off usually. However, if we dial it down just a little further, things never even complete. Now we are 9 minutes in compared to 4 minutes, and it's not even done, like we had to Control-C it. So we know that the process needs somewhere between 300 to 400 megabytes of memory to operate with reasonable performance. But finding the exact cutoff where the job performance goes down the toilet is a really tedious and trial and error process, right? It also only works when a job does this very fixed amount of work, reliably fixed amount of work, every single time it runs, like this example. But most production services are not like that. They respond to user input, they respond to the context. So to get an accurate number for services at scale that might have this very highly variable memory usage or memory requirement, we need a better way to do that. Enter SemPy. SemPy is a simple and self-contained tool that uses all of the technologies that we touched on so far in order to find out essentially how much memory does my application actually need to run. So in order to do so, it uses PSI pressure metrics, and it also uses memory.high to apply just enough memory pressure on a container in order to evict cold memory pages which aren't necessary for nominal workload performance. It's an integral controller which dynamically adapts to memory load peaks and troughs, and it provides a memory working set profile of an application over time. So it can be used to answer this question, which we want to answer, of how much memory does my application really need in any given point in time. So in this case, with the kernel compilation job, the same one as earlier, we can find that the answer for this compile job is actually something like 340 megabytes or so. But to get there, we just have to keep on pushing until we see pressure, because we are lowering memory.high, which is the throttling limit. And then we just keep on adjusting it as necessary, backing off and being more aggressive and so on and so forth. The script is only about 200 lines. It's not very complicated, but the technologies which it uses are the thing which I really want to focus on here. Earlier in the talk, I mentioned a team which had been for years believing, that their fleet host memory footprint was like 150 megabytes or so. And we found out using SemPy that it was about more like 2 gigabytes until their application just kind of fell on the floor and couldn't really do anything anymore. And it's highly reliant on these new technologies, memory.high and PSI, which we've been working on and improving over the past 5 years of Cgroup 2. We also use SemPy internally to, find regressions and leaks in a way which RSS measurements simply could never do. So it's a really important part of making sure that your systems are reliable and you understand how much you're loading them at scale. Earlier, we also touched a little bit on why memory and I/O in particular are so interconnected, because, for example, writebacks go through memory first in the page cache, but another reason is that we typically also do demand paging from disk. For example, the Chrome binaries code segment, where all the code lives, is over 130 megabytes. There's no reason for us on a contended system to load all of that up front. So on a system with little slack, we likely just load it with as gradually as possible. And that has ramifications for both memory and I/O as we buffer it in. For this reason, we really need to have control on I/O when we have control on memory. Otherwise, memory pressure is just going to always translate to disk I/O. Probably the most jejune way to solve that is by trying to limit disk bandwidth or IOPS. However, this doesn't usually manifest very well in reality. If you think about any modern storage device, they're typically a queued device. You can throw quite a lot of commands at them, and often when you throw multiple commands at them, you discover, you can get more bandwidth due to internal optimizations or whatever. And also the mixture of I/O also really matters. Reads versus writes, sequential versus random seek, the size, and so on and so forth. So this can really even apply on SSDs to some extent, and it's really hard to determine actually how much load a device is under, or what doing something to the device will cause in terms of device load. the cost of one I/O operation or one block of data is not uniform, and it really depends on the larger context of the request. It's also really punitive to make this, IO.max kind of way of thinking, where even if nobody else is using the disk, you have a fixed limit which you can never exceed. You can never go above n IOPS. You can never go above so many bytes of the disk in a second. And as such, it's not really good for this kind of best effort work on the machine with variable loads, where we do want it to succeed and make the best use of the machine resources when possible. So one of the first ways we try to avoid this problem is by using latency as a metric for workload health. So what we might do, for example, is to try and apply a maximal target latency for I/O completions on the main workload. And if we exceed that, we start dialing back other cgroups with LISA latency requirements back to their own configured latency thresholds. This prevents an application from thrashing on memory so badly that it just kills I/O across the system, or by doing so much I/O or such costly I/O that it actually starts to bite into the main workload. This actually works pretty well. It works really well for systems where there's only one main workload and you have a very clearly defined main workload and best effort stuff. But let's look at a multi-workload case as well, right? So here there are two high-priority workloads which are stacked on a single machine. One has an IO.latency of 10 milliseconds, the other 30 milliseconds. The problem is, as soon as workload 1 gets into trouble because it has the tightest latency limit, everything else is going to be throttled. That's the way IO.latency works, right? That's the way it works. We throttle people with lower limits until they reach their configured limits. So it's always going to get 30 millisecond latencies now. Again, that's fine if the thing you're throttling is just best effort, but here we have two important workloads which we want to prioritize. And IO.latency is great, therefore, if you have only one workload, but it's pretty hard to prioritize multiple stacked workloads in a reasonable way, because any not highest priority or not lowest priority workloads may be throttled too harshly. This is more like an API design concern, though, than a technical restriction. I mean, there are technical problems here, but it's mostly brought on by the way the API is designed. So how can we solve this? So our solution is io.cost, which might look very similar at first, but notice the omission of the units. These are not units in milliseconds, but a cost-based solution where you specify some weight for the cgroup. So how do we know what 40 or 100 or 60 means in this context? Well, the total of all three is 200. So in theory, if they're demanding the disk, or if they're all saturating the disk together, we're going to allocate best effort or slice about 20% of saturation capacity, workload 1 should get about 50% of saturation capacity, and workload 2 should probably get about 30% of saturation capacity. And just like IO.latency, this is work conserving, which means that if nobody is using the disk, if we're not saturating the disk, then anyone can use 100% of what's sensible for the disk. But disks are not that simple, right? How do we know when we're saturating the disk? How do we know what 30% of saturating the disk looks like? How do we know what 50% of saturating the disk looks like? So io.cost builds a linear model of your disk over time. It sees how the disk responds to variable loads and builds a model based on things like, read or write I/O, whether it's random or sequential I/O, the size of the I/O, and other things which allow it to build this model of how expensive is this I/O expected to be in the current system context. So it boils down this quite complex operation of how much latency or throughput does my application need, and boils it down to this simple weight-based prioritization system for overloads. And it doesn't suffer from the same problem as IO.latency, since you can stack workloads with this weight-based system, since it doesn't seek to penalize others based on you not meeting your allocated targets. It just wants to balance out the disk to reach its peak potential. This basic, it has a basic on-the-fly model which uses QDepth as a back-off mechanism. Start again with the basic. So io.cost has a few different mechanisms of operation. The basic on-the-fly model uses QDepth as a back-off mechanism, which works kind of okay in most cases. But for those who want more fine-grained control, we have this program called rescuddlebench, which is linked on the slide, which does quite detailed benchmarks of the disk and provides quality of service tunables to the kernel, which you can just copy-paste it from that application into this io.cost or QoS and tell io.cost how your disk behaves under certain kinds of load. This is a little bit more accurate since we're more able to closely inject load and measure the effects on the disk in a really controlled way instead of just doing it passively based on the I/O which you're performing at any given time. But whether you use the on-the-fly model or whether you use a QoS model, the weight system in general is fairly successful in simplifying the ongoing balancing of I/O significantly for users. So I've been talking about Cgroup v2 for a while now in this talk. I've also been talking about it for several years, different conferences, and historically the response I got to Cgroup v2 was, this is all very nice, but Docker doesn't support it, so what am I going to do? Nowadays we do have quite a diversity of container runtimes, and I'm pleased to report it's basically supported on more or less everything which is relevant. So even if nothing changes from your side, just moving to Cgroup v2 will allow your container manager to get significantly more reliable accounting for free. And we spent quite a while working with Docker and other folks to get things working and make sure things make sense there. Also very thankful to Fedora for making Cgroup v2 the default since Fedora 32, as well as making things more reliable behind the scenes for users. This also gets people's arse into gear. I think it was kind of a good signal to the industry as a whole that, if you are serious about containerization, if you want your product to be relevant, you really better support Cgroup v2 now. Like, the time has definitely come for you to support it or fade into irrelevance. The KDE and GNOME folks have also been really busy using cgroups to better manage their desktop handling. David Edmondson and Henry Train from KDE in particular gave this talk at KDE Academy 2020, and the title was Using Cgroups to Make Everything Amazing, which I won't dispute or try to disagree with that title in any way if they want to call it that. And it basically goes over their use of cgroups and Cgroup v2 in particular for resource control and interactive responsiveness on the desktop. This is definitely a developing space, but most of the major desktop environments now are investing in the space of resource control and Cgroup v2. And if you're interested in that, I definitely recommend giving their talk a watch. It really goes into the challenges they have and the unique features which Cgroup v2 has in order to solve those. Android is also using the metrics reported by the PSI project to detect and prevent memory pressure issues that affect the user experience on Android. Latency is especially important on platforms like this, and we need things like the PSI pressure metrics in order to keep the desktop responsive and keep the user happy. It would really suck, for example, if you were about to buy something and when you click buy, everything just completely froze and you have no idea whether it bought it or not. And that's one of the things which PSI can tell you, whether you are approaching the limit, whether you're approaching the edge, and it can take some action to resolve that ahead of time. So we've been working with engineers from Google and in other companies to use these pressure metrics that we created to more proactively prevent these scenarios and produce a more responsive and fluent experience for the billions of Android users worldwide. One thing I'm personally pretty excited about is that a number of the technologies which I've talked about in this talk allow us to do things as engineers that we'd never been able to do before at the operating system level. And this is one of the first times where we've presented, these as kind of a cohesive pack, as something cohesive to improve your operating system and improve your systems at scale. So I really hope that I've been able to help you think about how these tools and technologies might be able to help you and your organization and your projects and your services in a way that's relevant for what you actually need. I've been Chris Down, and this has been 5 years of Cgroup v2, the future of Linux resource control. Thank you very much, and have a great rest of your week.